Hello everyone. In this video, we're going to keep talking about exponential functions, but we're going to dive into why they're so useful. There are so many situations and scenarios that can be modeled using an exponential function because exponential functions have a really important property. And that property is that the rate of growth of an exponential function is directly proportional to the function value. Well, what does that mean? Well, I can show you what that means by just drawing a graph. So if I have an exponential growth function, we should already know what that looks like, right? It's starting flat over here and then slowly grows like that. And if you notice, the higher my function value, the steeper the slope. If I go even lower, the slope is even flatter. So the bigger the function value, the higher my y value, the steeper the slope is at that point. The rate of growth is faster. So can you think of any examples of scenarios or situations that follow this model? The bigger the function, the faster it's growing. Well, some common examples that you're going to see in your homework is interest, and that can be on loans or on savings accounts or checking accounts. Similarly, you could also think of it as like a return on investment. If you have an investment that returns a certain amount, all of these can be modeled using an exponential function because the more money you have invested or the larger your loan, the bigger the amount you have to pay each month, right? The bigger the payments because it's proportional to how much is in that account or how much is on that loan. Another great example of this is population growth. If you think about an animal population, the bigger the population, the higher the growth rate or the higher the birth rate because there's more animals to reproduce. So that rate of growth is larger as your function value gets bigger. And as we're going to see, really any growth can potentially be exponential. And so you'll see a few examples in the homework are different examples where the growth ends up actually being exponential growth. Well, as we saw from the previous chapters, exponential functions with base e are really, really useful. And so those are the ones we're going to focus on today. And so there's something important to keep in mind with that. Exponential functions with base e represent continuous exponential growth. And a great example of this is population growth. If you have a population of animals, they're not only growing once a month, or the population's not increasing only once a month. It's continuously increasing as animals have babies throughout the year, right? So those type of exponential functions you can model with base e. When we think about finances, this can happen when you have interest that's compounded continuously. Maybe you've heard of that before. But if it's compounding continuously, you can use base e. So with all the examples in this section, we're going to be using base e, which means all of these exponential functions can really be written in the same form. This n is equal to n naught. That's what this little o is, or 0. N naught e to the kt. Remember, e is a irrational number, so that's a set value. That's not changing. That's not a variable. N naught represents my initial value. T, of course, is time. And k is your rate of growth. So if you think about interest, it's your interest rate. Population growth, it would be the rate at which your population is growing. And then n, of course, represents your function value, or the actual population, or the actual amount in your account. And so with so many of the homework problems, it really just boils down to using this formula. Can you plug in numbers where they're supposed to be plugged in? You may have also seen this form of the equation, p e to the rt. This is the same type of equation, just with a more financial focus. P represents your principal amount that you invest, r is your interest rate, and t is still time. It's the same exact equation, though. All you're doing is you're just changing the variables. So either of those work. Whichever one you're more comfortable with, you can use either of them throughout this section. Well, one interesting thing that's true about exponential functions is because of this property that we described earlier, we can generalize exponential functions using derivatives. So based off this definition, I could write this. The derivative, or the rate of change, of an exponential function is directly proportional to the function value. That's what that definition above says. So this is another way that I can write exponential functions using derivatives. What's true about this k? Well, the reason why I use the letter k, that ends up being your rate of growth. The same k that's in your original function. And there's a reason why. Now that we understand how to take the derivative of this function, we can actually calculate this ourselves. So if I take my equation, n equals n naught e to the kt, and take the derivative, so if I take the derivative of both sides, on this left side, of course, I just get the derivative. And on the right side, remember, n naught's not my variable. I'm going to treat that as a constant. And so I can pull the n naught and just take the derivative of e to the kt. Well, I know how to take the derivative of that, and so I get dn over dt equals n naught. This derivative is just k e to the kt. Now, because multiplication is commutative, I can switch the order around, and I get k times n naught e to the kt. And what's true about this right here? That's my original function. What is that equal to? That's equal to n. And so this is where we get this derivative form of my equation. So if you see that, you can instantly tell what the rate of growth is just by what that constant is that's being multiplied by your function. I will say though, what does this not tell you about? This does not give you the initial value. And that's because this property is true regardless of where your function starts. It's always true. It doesn't matter what your initial value is. So that's really the big ideas for this section, but there is one more thing that we need to talk about. If we're talking about growth functions, something that's commonly calculated with growth functions is something called doubling time. And the concept behind this is pretty straightforward, right? This is just the time it takes for an exponential function to double. And the reason why we want to talk about this concept is because doubling time really only depends on one thing. It only depends on the rate. It doesn't depend on your initial value at all. And I can actually show you because we actually have a formula for doubling time, and I'll show you how we can get that. So if you have an exponential function, and I want to calculate, okay, how long is it going to take for my value to double? Well, first off, that means I'm going to be solving for t. And what do I want to set my exponential function equal to? Well, if I want my initial value to double, if I want that value to double, I'm going to set this equal to 2 times n naught. And now I can solve for t. Well, the first thing I'm going to do to solve for t is I'm going to divide by n naught on both sides, and notice what happens. Those initial values cancel out on both sides, and all I'm left with is 2 equals e to the kt. Notice how this does not depend on the initial value anymore. And so therefore, it really only depends on the rate. Well, how do I solve this if t is still in my exponent and I'm trying to solve for t? This is where I can just take the natural log of both sides. I get natural log of 2 equals natural log of e to the kt. I can use my natural log properties to know that the natural log and the e just cancel out. And I'm left with natural log of 2 is equal to k times t. I'm going to solve for t, and I get natural log of 2 over k. So this is my official doubling time formula. And you'll see this on your formula sheet. But in order to find the time it takes for your function to double, so that's what capital T sub 2 means. It's the time it takes your exponential function to double. You just take the natural log of 2 and divide it by your growth rate. And that's it. Okay, so that's really all you need to know in order to go ahead and start on the 3.3 assignment. Go ahead and give it a shot, and then I will go through a couple problems in the examples video. Thanks, guys.